Okay, we're continuing on. The radius of a sphere. Well, spheres look like this. Again, this is a rough graph. Don't judge me on that. Just get a rough idea. The deal is they only depend on the radius. The radius of a sphere is increasing. The RDT is 1 meter every second. Now, here I provide the formulas for whether they want the surface area or the volume. Volume is 4/3 pi r cubed, and surface area, the surface of the surrounding, is 4 pi r squared. Here they say find the rate at which the volume is increasing. How big is the volume changing when r is 20 meters? Well, we know that the volume is 4/3 pi r cubed. And since everything is being changing with respect to time, I take the change of rate with respect to time. That gives me dV dt equaling. Now, this is a constant. Bring the 3 down. They cancel out. I'll write that in 2 steps. 3 r squared dr dt. Okay, I have to write a bit nicer. The 3's cancel out. And I'm looking at dV dt equaling 4 pi r squared dr dt. So the change of volume with respect to time will be 4 pi. I know the radius is 20 and the RDT is 1. You could leave the answer like that out of mind. The units are, for volume, the cubic units per second, or dV dt if you really wish. That's 400. 400 times 4 is 1600 pi cubic meters per second. You could plug that in a calculator, give me that. I really can care less. If you get this far, me and you are very happy. How about here? We're dealing with a triangle. Well, let's draw a triangle. Suppose you have one of these triangles. Now I'm going to draw scaling, which means I'm not making any assumptions that it's an isosceles or equilateral, but here it is. Any triangle. Suppose the base of a triangle is shrinking. Well, a triangle depends on a height and a base, and the base is perpendicular to the height. The base of a triangle is shrinking, so the change of the base with respect to time, if it's shrinking, it's negative at a rate of 1 centimeter every 1 minute. And the height is increasing. The height is increasing. It's positive at 5 centimeters every 1 minute. Find the rate. So we're looking for the rate at which the area, how fast is the area? Oh, that's an ugly D. How fast is that changing when the height is 22 centimeters and the base is 10 centimeters? Well, the formula for area is 1/2 base times height. Since we have information about all of those, we simply take d dt right away. Normally, we might have to get rid of one of those, but we have information about the height, the base, the change in the height, and the change in the base. Here we get the ADT. Now, 1/2 is a constant. I need to use the product rule. Derivative of the first, that's the BDT times the second, plus the first times derivative of height is the HDT. And this is straightforward. The hard part is the product rule. Besides that, everything's given. That's 1/2 times dBdt. The change in the base is -1. The height is actually 22. The base is 10 right there. And the change of the height, which is 5. Now we need to know, is it getting bigger or smaller? So that is 1/2 what? -22 plus 50. Well, obviously, this is increasing. -22 plus 50 is that 28? Half of 28 is 14. You can do that in a calculator. Centimeters every minute, since it's area, centimeters squared every minute. So if you do this, if you decrease the base by a rate of 1 centimeters per minute, increase the height at a rate of 5 centimeters per minute, the area will be increasing at a rate of 14 square centimeters every 1 minute. We have another triangle problem. I'm going to pick what they have. It looks like an equilateral triangle, but it's not. Unless they tell you that, you can't assume it is. Again, it depends on the height. The height is perpendicular to the base. That's always the case. And let's see how that works. A triangle has a height that is increasing at a rate of, the height is increasing at a rate of 2 centimeters every 1 second. And its area is increasing as well at a rate of 4 square centimeters every 1 second. Find the rate at which the base of the triangle, how fast is the base of the triangle changing when the height is 4 centimeters and the area is 20 centimeters. Again, they gave us everything here, centimeters squared. So where we start with combining those. Area is 1/2 base times height, and the same, hopefully this is getting old. If I take the rate of that with respect to t, I'll get dA dt equaling 1/2. Now here the product rule, derivative of the first, that's dB dt times the second plus b times dH dt. Now if I fill in what I have, here I have things slightly different. I have area to be 4. This is 4. This is 1/2. dB dt is what I'm looking for. I could have solved for that, but if you put in numbers, it's easier to deal with numbers than variables. H is given to be 4. I could only use H when I take a derivative. B is given to be, though I'll get to B in a minute. dH dt is 2. Now I need to find B. Well, let's think about it. A equal 1/2 base times height. If the area is 20 and the height is 4, then can't I say 20 equal 2b? Doesn't that mean b equal 10? And there it is. If I multiply by 2 both sides, I'll get a to equal dB dt times 4 plus 20. Well, it's a linear equation. Subtract 20 from both sides. So if I subtract 20 from both sides, I'll get negative, is that right? Yeah, negative 12 equal 4 dB dt. So the change of the base with respect to t will be negative 3, and the units will be in centimeters per second. Obviously, the base is decreasing when this is happening. Okay, I'm changing number 26 in the book. This is not 26 in the book because none of the homework problems relate to it. This is more like it. So this is like 25, 27 will be like our 28, and so on and so forth. Again, I worked out that problem and then I noticed that there's nothing like it. Let's talk about something like the homework. For the following exercises, consider a right cone that is leaking water. So let's say the cone looks like that. It's leaking water out. So it has some water. And it's leaking water out. Now it says the dimensions of the cone, it is 16 feet high and the radius is 5. But that doesn't represent the liquid in it. Now, 26, how fast does the depth of the water change? They're looking for dH dt. when the water is 6 feet high, when the height of the water is 6 feet high, if the cone is leaking at a rate of 6 cubic feet per minute. So the change of volume of this cone is 6 cubic feet every minute. Let me elaborate really quick. As the water starts leaking out of this cone, you'll notice that in the beginning, it's going to be going down a lot slower. As time passes by and there's less liquid, the water level, the height, is going to be changing very rapidly. So here, the height will go down a lot faster than here. Well, what do we know about the volume? The volume of a cone is 1/3 area at the base times the height. Now again, these formulas I provide, since this is not a prism, I'll give you that. So if I know the volume is pi over 3 r squared over h, I notice there's nothing about r. They told me find the change in the height when the height is given and the volume. R, there's no information about it. I need to get rid of that. And the way I do that, I would take, this is 5, this is 16. The change, the height of the liquid and the radius are unknown. These are similar triangles, so I could say 16 to h equals 5 to r. Of course, you could write this ratio 6 different ways. If I cross multiply, I'll get 5h equals 16r. And here you make a decision. Either you solve for r, get rid of r, for h, whatever you want. Since the information given is all in terms of h, I want to leave h in the problem. I want to get rid of r. What would r equal in this case? And that's how you decide which way to go. R is 5h over 16. Take this and put it in for r. And now my volume is in terms of h only. That's 5h over 16 squared times h. So now I would say my volume is pi 5 squared 25 over 3 times what is 16 squared? Is that 256 over 256? This is h squared times h, that's h cubed. And once I have it in terms of what I want, all what I do, the tradition, take that change with respect to t, dv dt equals 25 pi over 3 times 2, and of course you could multiply those. The derivative of h cubed is 3h squared dh dt. Now, if I move this to the right, and if I look at this problem, I know that dv dt is 6. 25 pi over, the 3's cancel out, 256, h squared, I know what h is. H is 6 squared dh dt. So if I cross multiply, 6 times 256 divided by 25 pi times 6 squared is dh dt. You could leave the answer like that. You just have to give me units. If volume is changing at a rate of cubic feet per minute, then the height is feet per minute. Of course, you could clean that up a bit if you wish. Or you could say that's cancel with one of those. You could multiply those out. Again, it makes no difference. 256 over 6 times, oh, that reduces. Well, here, minus well. Take 256 divided by parentheses 25 times 6. That's 128 over 75 pi. (128 over 75 pi. That will be the answer in the back of the book. You want to approximate that by a calculator? Knock yourself out. It's all good. It's the same thing. And we're talking about another problem of these types. A vertical cylinder. Oh, now that's slightly different. A vertical cylinder. So we have a cylinder. Cylinders look like that. Those are prisms. Is leaking water at a rate of 1. So the change in volume with respect to T is 1 cubic feet every 1 minute. So you're dropping down some water out at a given side. It says if the cylinder has a height of 10 feet, so this height is 10 feet, and a radius of 1 feet. Okay. At what rate is the height changing when it is 6 feet high? So when the amount of liquid in is 6 feet, a bit more than half, how fast is the height of the water shrinking down? Well, we know the volume here is area at the base, which is pi r squared times the height. But here, it's a bit better than that because we know that the radius is fixed. It's always 1. That doesn't change. So the volume is nothing more than pi h. Here, I don't have to make that connection and get rid of the radius because it's fixed. It's not changing. And if I take a derivative with respect to time, I'll get dv dt to equal pi dh dt. Well, dv dt is 1. This is dh dt. So if I divide both sides by pi, guess what? Dh dt will end up being 1 over pi. It's independent of the radius because the radius is fixed in this case. And the units for the height, if we're talking about volume being cubic feet, that's feet per second. So it's a lot simpler than a cone. Cones and pyramid are a bit of a challenge. And I have a nice problem I wanted to do for you. I wanted to make sure you see one of those. Okay, a trout has ends in the shape of an isosceles triangle. What we know about isosceles triangle, these sides are equal. And it says the height is 4 meters and the top is 3 meters. Okay. So it has a width of 3 meters and a height of 4 meters. And the trout is 10 meters long. Okay. Water is being pumped into the trout at a rate of, so the change of volume with respect to time, you are pouring in 5 cubic meter every minute inside of this. At what rate does the height of the water, so water is this high, if you're pumping water into it, that height is increasing. They're saying how high, how fast is that changing when the height of the water is 1 meter, when it reaches 1 meter in depth? Well, what do we know about this? This is a prism. If you stand this on its side, it looks like this. Anywhere you cut parallel to the base, you get the area of the base. That's volume is area of the base, which is a triangle, 1/2 base times height times the 10 that's fixed. So the volume is 5 bh. Well, let's talk about the base and the height. Obviously, everything in terms of the height, I need to get rid of the base. And let's do that. If I look at the base of the liquid is right there. So if I look at, oops, this is the liquid. That's this, right? Call this the base. Call this the height. If I extend that, that's the whole thing. That's 3 meters and that's 4. These are similar triangles. So if I take 3 to the base, that should equal 4 to the height. If I cross multiply, 3h equal 4b. And if I want to get rid of b, I will say b equal 3h over 4. And if you wanted to get rid of the height, you would have said h equal 4/3 b. So this is 3h over 4. So the volume is pretty much 15 over 4 h squared. And the reason for that, this height is fixed. Now if I take a derivative, dv dt will equal, now the 15 over 4 is a constant, derivative of h squared is 2h dh dt. dv dt will equal 15 over 2h dh dt. Let's fill in the blanks. We know that volume is 5. The height is 1. dh dt will be what? Well, dh dt will be 2 times 5, 10 divided by 15, or simply 2 divided by 5, 2/3, and the units for the height will be in meters per minute or second, I forgot. Per minute. The units for time is minute. And that's pretty much how fast the water level is rising at that time. There's the homework, and that pretty much concludes this section.